Okay, good afternoon. Welcome, everybody. Just want to allow a few more minutes to give a few more folks a chance to get dialed in here. So everybody just sit tight for a moment. We'll give it another minute or two. Just a note while we are getting started here, there will be a couple of housekeeping reminders that I want to kind of open with. So as soon as we see a couple more people dialing in here, we'll just keep tabs on that. One thing that I'll just note is that everybody who's joining is joining with mute and camera disabled and mute on. Will allow people to submit questions using the Q&A tab at the top. There's a small button at the top of your screen. It says Q&A. Go ahead and enter any questions or comments you have there, and we'll compile everything at the end and try to address as many of those as we can while the time allows. Like a couple of folks are still joining. I think just in terms of time, why don't we go ahead and get started, and as more people end up dialing in, we'll let them jump in midstream. Okay, we are recording this event. We will be able to make a recording of the entire webinar available offline for review if you want to share that with colleagues, a review at the end. So just keep that in mind. And with that, why don't we go ahead and get started by sharing my screen. We'll do this kind of as a tag team event here. So, okay, can you see the screen now? Emil, maybe just a quick confirmation. Got it? Okay, good.
Thank you.
Great. Great. Well, thank you. Again, thanks everybody for joining. On behalf of Brave Scientific and Insight Chips, we welcome you to this look at the liquid cell TEM holder and a quick live demonstration on microscope. So this should be pretty interactive. We'll start with a couple of background slides, and then I'll pass it over to the lab where we can see some hands-on tutorial. Okay. So again, as I said, thanks everybody for joining. Rave Scientific, the U.S. Entity here, partnering with folks from Insight Chips to talk about the nanochannel chip today. As you can see, we'll talk a little bit about the Rave background, do a quick overview of the Insight Chips technology, and then we'll turn it over to do the live demonstration. If there's time, as I said, we'll do Q&A at the end. So ideally, you'll have a better understanding of how to handle the liquid cell chip and how to use this for atomic level resolution characterization. All right, so from the local entity, Rave Scientific here, myself, Kyle Crosby. You can see I'm based in northern Vermont. Picture kind of gives it away in the background. Background in PhD in materials engineering, and together with my boss, my colleague Jeff Strager, we are handling a lot of accessories, chamber accessories, in situ accessories, sample prep on the front end, everything that kind of revolves around the electron microscope. Jeff and I worked together for more than a decade at Zeiss. And let me try to adjust that audio, see if I can get it dialed in over here. Apologies for that, folks. So you can see a small team based out of Bedminster, New Jersey. Wanted to highlight just a few of the brands and vendor partners that we have and some of those technologies that they represent. As you can see, most of what we do revolves around the electron microscope. You see Zeiss, Carl Zeiss at the center there. We do still represent Carl Zeiss for electron, FibSem, and X-ray technologies. And most everything else is going to either be feeding samples into the electron microscope or supporting onboard workflows. The two that are a little bit standalone are the XM mass box, which is a laser ablation, laser ionization time of flight system. And we also offer very compact handheld Raman systems from Light Novo. So I'd encourage you to go ahead and check out our website. You'll see more information about all of these, as well as our web shop where we have access to more than 2,500 products there. Quick overview, just a snapshot of our markets and customers. So we do cover all flavors of different application space and different customers: industry, academia, national labs, life science, material science, semiconductor, a little bit of everything. So we have resources, know-how, and connections into those different industries. As mentioned, microscopy systems. So Jeff is still covering Zeiss in the Mid-Atlantic territory. We know this group very well, so please reach out if you have any questions on that front. In terms of TEM solutions, we're going to talk today obviously about the Insight chip and the liquid cell holders, but we also offer in situ holders for cooling, heating, electrical biasing, vacuum transfer, all of these different technologies out of Melbuild. And from Nanomegas, we're talking precession electron diffraction technologies, which really enhance your TEM capabilities. And often with that, we would partner or pair that with something like a direct electron detector, for instance, the Merlin camera from QD. Again, just a note about a couple of the standalone systems. This is the time of flight mass spectrometer here on the left. Benchtop system, very easy to integrate, super user friendly. On the right, here's the compact Raman spectrometers. Again, you can see small enough to fit in the palm of your hand, great for field utility, very robust, very ruggedized for environmental. On the sample preparation side, we have sputter coaters, carbon evaporation systems, critical point dryers, a variety of different plasma treatment and cleaning options, a system that does plasma, UV, and heat cleaning in one. We also have plasma cleaning and vacuum storage for TEM. Again, happy to have offline discussion about any of these technologies. Reach out anytime. And then as mentioned, we do a lot of other things that are a little bit more hands-on service in terms of customers shopping on our website, and these are more of your standard EM lab supplies that you see here, sputter targets, emitters, calibration samples, etc. So that was a pretty quick overview of what I'm up to. I'm going to ask that I'm going to stop sharing quickly and then pass off control to the founder and CEO of Insight Chips, and we will ask Emil to give us the rundown on the liquid cell nanochannel and the demonstration. Thank you.
Absolutely. Thank you, Kyle. And if my audio is giving out, I don't really see much on the screen since I'm presenting, so just let me know if there's anything, Kyle.
Sounds good. Sounds good for now.
So Insight Chips, I know some of you attending have heard of us before. I can see I know some of you. So thank you to everyone for tuning in. It's a pleasure giving this webinar. I stay up late here in Denmark to do it. It's actually past my bedtime now, but it's something I have been looking forward to do. And I appreciate you coming on. Insight Chips is a very young company. For those of you who do not know us, at least not very well, we're 4 years, I think a couple of days ago, actually. It was just our birthday. And we are also a small team, roughly the same size, I think, as Rape Scientific. And we're very focused on our core technology, which is the nanochannel chip. It says atomic resolution liquid cell TEM here because the very core of what we enable that differentiates us from the last 25 years of liquid cell TEM research is high resolution. And in fact, just to show a few examples here, and we have a growing portfolio of many more examples, we can actually obtain atomic resolution in our liquid cells again and again and again with a multitude of samples, whether it's metals or MOFs or soft materials. We really enable a new level of research by introducing high resolution reliably. And in this slide deck, I'll explain to you a little bit about why we're different and what is the technological differentiation that allows for this. So to tell a story of where we're coming from, we can actually go about 16 or 17 years back into Professor Christian Mølhave's research. He's a professor at DTU in Denmark, and that's where we also founded as a company. Christian, he was making this type of chip himself that you can see in the bottom left corner. And many people have made this type of chip over the last 25 years. In fact, it's the only type of solution that you've been able to get commercially for the last 25 years. We refer to it as a clamp chip. You can call it a sandwich chip. I know none of the other companies call it that, but you basically do sandwich in the liquid between two chips. And those chips have membranes, and in that way you make a sandwich of liquid. And if it's thin enough, you can see through. And what you can see in the sketch here as well is that the membranes tend to bulge outward. So there's this effect, the bulging outward, is because of the vacuum in the TM. And then if you imagine a TM sample, a good one is maybe 100 nanometers thick, give or take. But assembling something with your fingers that is 100 nanometers, you know, you'll have to be very, very lucky in order to get that. Sometimes you do, but most times you do not. And whatever you get, you never know what it is. And it varies across the membrane because it's bulging. So even though it was a great innovation to introduce liquids in this way, you've never had liquid thickness control ever until now, because Christian, he grew very frustrated of this because he made these chips himself. He wanted high resolution, so he invented the nanochannel chip. So just to summarize, Christian grew frustrated with a number of things. Even though the system was advanced and you can actually do electrochemistry and you could do liquids for the first time, you had the membrane bulging. You couldn't control liquid thickness, and therefore you couldn't get high resolution. Also, Christian struggled a lot to prepare the chips. You have to practice a lot to get good at it. And even then, it takes an hour or more to prepare. So it's time consuming. And because the sandwich chips are open until you use them, they get contaminated until you're using them. So that was also an issue. And finally, he discovered that even though the flow should go nicely over your sample in the field of view, the way you put together the chips actually made the flow very unreliable. And sometimes it would go kind of around the chip, around the membrane in ways you didn't see. And it was hard to predict and make reliable. And you could not mix liquids in the field of view. You could only mix liquid outside the chip and then flush it in. So all these difficulties motivated Christian to start working on a new chip. And ta-da, the nanochannel chip as a new concept emerged. And the nanochannel chip is literally means a chip made of one piece. The difference here is enormous because you no longer have to assemble anything, it's already assembled. And the liquid thickness control that was never there before finally is here. We can actually control the liquid thickness with 10 nanometer precision, whether it's 5 nanometers or 50 or 500 or 5,000. It doesn't matter what liquid thickness you want. Inside chips can make it exactly that again and again and again, hundreds, if not thousands of times in a row. We can also make silicon nitride membranes that are thinner. We can do down to 10 nanometers. We've done it before and the chips are working fine. But our standard production is 15 to 20 nanometers. And we slowly push it down as we feel comfortable in the production to do it reliably. So I think we, in the future, will be between 12 and 15, but we'll see. The point is we're really advancing on the thickness, both of the liquid and the membranes. The way the system works is you have, of course, your TEM holder. We also have SEM holders, but that's a different conversation. But your TEM holder has some O-rings inside. There are 4 of them because the chip has 4 inlets. Those inlets are used to create 2 bypass systems, 2 inlets where the liquid comes in and 2 for the liquid to go out. So you have a constant flow inside the chip if you wish. And this can be used to mix liquids in the field of view because you can inject 2 liquids at once into the holder. The way it comes into the chip is via the holder because it has tubing inside. So the structure to the left, or the sketch, you can see there are inlet ports, 1, 2, 3, 4, and they correspond directly to the chip. If you look a little closer on the chip, you can see the membrane is in the center of the chip. So the internal bypass structure you actually don't see. You know it's there. That's how we make it, but you never see it because it's wrapped in solid silicon. What you do see, however, is this transparent window. And all of what you see in this optical image is made of nitride. Of course, to the edges, you can see some solid silicon that you cannot see through, but everything in the center with the nanochannels it's nitride. And in the optical image, you see brown lines, and those are the nanochannels. Everything is nitride, but the brown color comes because there's a separation between the membranes in those areas only. So everywhere where the membrane is this more bluish gray color, that's where the membranes are bonded and you don't have liquid. So in the bottom image, you can see what it looks like in the TM with this exact design. Of course, in the TM, you don't see anything if there's no liquid because nitride looks the same everywhere. But in the image here, you have water filling the channels. So you can actually see the exact pattern of the channels look like this in the TM. There are various ways to use the system with the liquid. One is to flow it in, and quite often we use a syringe, like you see in the image to the left here. We have the holder inserted, and via the ports, we inject via a syringe completely manually. And this is because a lot of cases are about either in a qualitative way adding liquid or exchanging liquid. So you could get a little more detailed and quantitative if you used a pressure-based flow system. Then you can have reliable flow rates and repeat your experiments if it's dependent on that a little bit better. But in the video to the right, you see in how just a few seconds it takes. Once the liquid touches the chip, capillary forces are responsible for pulling in the liquid, and all the channels fill extremely fast. Another way to use the chip is by adding the sample before you load it into the holder. And this is what I'm going to show you in the lab today. I'm sitting here by the TEM, and we're actually going to do this once I'm done with my presentation. And here you can see how the capillary forces are working to pull in the liquid in the chip. The particles are introduced in that way if it's particles you're loading, but it could be any liquid. And then you simply put it in the holder and insert it in the TM, and you're ready to go. I want to share one advancement we made in our chips last year because this was very important for us. Normally, when we inject liquids with particles in the way you just saw, the particles would flow through the channels and be gone from one bypass to the other. So we created a system where geometrical confinement traps the traps the particles where we want them. And it's very simple not to make. That took years to figure out, but in the concept, it's simply by making the channel thinner in one region, so a particle can enter but not go any further than the confinement. And in the right side here, you see a almost extreme case of trapping particles where 1,000 particles is trapped in one channel. And you can see how more shallow channels go to all the sides that continue to provide liquid and new sample to this channel as long as you keep flowing them in. One thing that we need to do as well today is we need to open the inlets of the chip. And this comes back to the frustrating part about the old system, which had contamination quite often inside the channels. But with our system, you actually have a nitride membrane sealing all of the inlets, which means that no matter how many months or years you leave your chip on the shelf, it doesn't experience air except the air that's inside that comes from the clean room. And this means that the inside, which is all covered in nitride, is still very hydrophilic. It's still very clean until you break this membrane open, which we do with a needle, and I'll show you exactly how. So we have a few products, and one of them is just coming out. So we have 3 holders, Atomus, Alpha, and Volta. The Atomus is what I just showed you. We walked through how the chip works, but the Alpha can do the exact same thing. It works the exact same way, but we made it long and thin and slim so we can tilt more. And we made this specifically for tomography or 3D electron diffraction. And a specific case is also good to mention that is it's compatible with Atolite's system, which is a cathodoluminescent system. And not a lot of holders can do that because it needs to get very, very close to the field of view. And if you have an in situ holder, typically you have something in the way. So we created this solution which works for that. And then something I cannot share a lot about right now, but we hope to launch in about a month is our new electrochemical system. We've been working on this for years in secrecy, because we think it's a big deal to be able to do electrochemical experiments with atomic resolution. And we already have some atomic resolution results, and hopefully many more coming over the next couple of months. So that's just something exciting to share. And finally, we have a heating system where you heat up the tip of the holder in a bulk manner. It's not on chip heating, it's the entire tip you see there. And we can do that up to 120 degrees. So this summarizes all the features we have. So I think with that said, I can either take some questions. No, I'm not done yet. I just recall now. Just to share some experience or some inspiration from the customers and the test cases we've had so far over the years. The top applications are what you see here. To begin with, we have some examples here with crystallization or nucleation. And the case you see to the left, that's where we mix calcium chloride and sodium carbonate to create calcium chloride. And that's done by our customer in Japan, who wanted to study the growth using diffraction in our channels. And this works very nicely and was quite repeatable. So this was actually from the first day of using the system when I wasn't even in the lab. So they really found out how to use this quite easily and got good results straight away. And the other example here is a paper by our other customer at PNNL, Pacific Northwest National Lab, I think it is. They've had our holders for many years and made this paper you see here. And then there's MOFs, which step into an interesting domain because a lot of MOF research has been done so far, but it's difficult to do if you don't have high contrast, high resolution. So as you can see here, we can actually see high resolution details of MOFs, not only in a static way that you see to the left, but as you see to the right, we can see the dynamic growth of MOFs with atomic resolution. Of course, there's a lot of beam effects in the case you see to the right here, but it simply demonstrates that the resolution is there and the MOF structures are still intact, at least in some ways, during this video, because you can see the structure from the diffraction spots. The alpha holder we made can tilt a lot. You need 4 millimeters of pole piece clearance, and then you can tilt plus minus 70 degrees. This is an area we look forward to getting more results in. So far, there's the paper you see to the right here, which actually was done with the first holder we made, the Atomus, which could only tilt about 30 degrees. But it shows that doing 3D ED in liquids, or micro ED as I think it's more commonly called in America, is possible. We can maintain the high resolution even when tilting, and now we can just tilt even more than we used to. Finally, there's some spectroscopy that's possible. I know that since liquid thicknesses were always difficult until now, actually getting good EELS data and good 4D STEM data was always a challenge. But we have several customers using it quite frequently and operating with EELS pretty much completely normally as if they had a dry sample, not really concerned that it's a liquid sample they're dealing with. So this is just showing that there's an entirely new spectroscopy research branch that can be explored even further with great resolution that wasn't possible before. So I think with that said, that's all I needed to present now. So I'm curious if there are any questions.
I'm not seeing anything yet, but please, yeah, go ahead and proceed. We'll make sure that we give time at the end for them.
Absolutely. In that case, we can just move straight ahead. So I hope you can all see the screen that's displaying the holder on the table here. If there's any issues with that or we need to change, it would be nice if you could write it in the chat just so I know how to make a change, make it a little bit clearer for you. I can also hold things closer to the camera, so hopefully it becomes a bit clearer to you. So just let me know. What you see here is our sample holder, or one of them. This is the Artemis, and it's a new, it's our newest design with only 2 screws, and you actually only need to remove one of them to put in the chip, because one of them is kind of, it's in a slot that's not completely closed. So as long as you just loosen it up, you can slide out the lid as long as the other screw is removed. So hopefully, as I'll demonstrate, if I don't mess it up, you'll see how easy it is to remove this lid and place the chip and screw the lid back on. And that's what we're going to do now. So it has the one screw that we need to remove fully. So I'll just do that. And then the other screw, I'll just loosen it up a bit. So then with the tweezer, should be able to just slide out the lid here. And I can place it down here for later. So down here, you see the chip. There's a chip from an old experiment, and I typically do store it in that way, because then you know where the O-rings are and you don't get any dirt inside. So I flip the chip out, and I can see that some of the O-rings got stuck to the chip. I'm just going to put those back in. The O-rings are quite small. I don't know. You can probably not see them on the screen here. They're about 1 millimeter in the inner diameter. So you can get them smaller, but we are approaching how small O-rings you can comfortably make. All right, O-rings are back in. Then I'm gonna grab a chip. And we're gonna puncture the membranes. I forgot the needle, so let me just get that. The needle we use is also a pretty small one. I think it's gauge 34 or 36. So it's a quite tiny, pointy one. And how to do it is just to insert it into each of the inlets. I've already done 2 of them, 3 now, and done. So it really just requires you to put it in there and touch the membrane, because it's so thin nitride that any touch you can do with your hands surely will break it. Now, I have some sample here. This is a mixture of different gold nanoparticles. We have some 20 nanometers, some 50 nanometers, and some 100 nanometers. And I'll just take a droplet of this. I don't need a lot at all. If I had a pipette that could give me 100 nanoliters and I could control it well, that would be fine. In order to put it in the chip, I actually don't even want to press out the liquid. I just want to make sure some of it is protruding from the tip of the pipette, because then it will transfer to the chip once it touches. So again, you probably cannot, if you believe it, maybe you can see there's a droplet kind of glistening on the chip on one of the inlets. Or maybe not. But the liquid is there, I can promise you. Once it's there, you take the chip up and you flip it over. So the inlets are now facing down towards the O-rings in the holder. It's now in. It has a nice groove, so you can just kind of dump it in and it falls into place. You slide the lid back on and screw the screws back in. That's it. We've just prepared a chip. This one has a liquid thickness of 240 nanometers, and then it has traps as well of 44 nanometers. I hope that we see a little bit of all the particles we have in the mixture. The holder is pumping now. So we have 3 minutes until it's pumped. And now is the time for questions, if any of you have any.
Yes, actually, there is one in the Q&A now. So maybe we can address this while we pump. So the question is, what is the part made of for the flow of the fluid in the holder? Would it affect, for instance, corrosion studies? Is it reactive? And how would this be comparable to corrosion in macro samples or bulk samples?
Good question. As of yesterday, we actually can make different materials. We've always used PEEK tubes, which are quite robust chemically, but the issue with that is that we need to use epoxy to fasten them. And epoxy is not great for many chemicals. Of course, they are great for some, but when it's not good, you're just kind of stuck without any other option. But yesterday we did our first test with welding metal tubes into the tip. And this opens a whole new world of possibilities for us, because what we did yesterday was stainless steel tip and stainless steel tubes. But I can imagine we can go in titanium or brass or aluminum. And in the future, our users could simply select what material they have. It's a little early to promise that flexibility entirely, but it seems like that is possible.
Great question. Thanks, Mohammed, for that question. Very good. Maybe just a note about the biasing capabilities. Can you talk a little bit about the sort of voltage range that you have access to in terms of the biasing holder?
Yeah, we have a minute to pump, so why don't I just show you a little bit of preliminary data?
Perfect.
The system we have now, as the very first prototype, only had 2 electrodes. So you see 2 nanochannels here with electrodes inside. You barely see the electrodes because they're made of carbon. We're also going to explore other materials. The next one will be platinum, but the first one was carbon. And now the channels are full of a liquid. I believe this is copper sulfate. So you can see once you start applying bias, this was a cyclic voltammogram between -2 and +2 volts, if I'm not mistaken. You can see you start growing your crystals here. And even when you grow from the opposite side, you can see the other electrode is hidden down here inside the solid silicon. Just going to insert the holder. Yeah, so this is what we've done so far. And we do have some atomic resolution data with this experiment somewhere. Maybe I can find it. Or maybe you'll need to wait for us to publish it very soon, because I don't see it here. But our new system has 3 electrodes. We're going to do carbon. We're going to do carbon first and later platinum electrodes. And we'll do down to 40 nanometer liquid in the new prototype we just have out of the clean room. So we'll be able to truly get some high resolution data of electrodeposition and hopefully some electrocatalysis and other electrochemistry experiments. We're very excited. Are there any further questions, Carl?
I think that's good at this time. Go ahead. Please proceed if you're ready to go.
Okay. All right, so we just spent a couple of minutes loading the chip. Now it's in the TEM. I'm just going to turn this off so I can see where the beam is. Yeah, I'm going to the same place that I had in earlier, because although it was a different chip, you tend to have the membrane quite exactly in the same place every time. And that's what I just found now as well. So we have the chip here. I can see that there's some misalignment or some Z-axis correction. So I'm just going to do that here. And typically you can just tell that by that ghost from the crystallinity of the solid silicon on the side. So now it's aligned in the Z-axis, and immediately I can see particles in the channel here. I don't know if you can see them. What's the feedback? Can you see particles yet, Kyle?
Yes, right there. Perfect. Yes, definitely.
Okay. So I told you we had a mixture of different particle sizes. So you can see there are some big ones located in the bottom of the screen here. Those are 100 nanometers. And then we have some small ones that made it into this trap region. Even though the particles are only 20 nanometers, they are still getting somewhat stuck in the 44 nanometer channel. It doesn't really drive them through with a large flow. So this is really the most optimal conditions you can ever get for seeing particles, because they have minimally liquid around them. And I can see those crystal ghosts that are just jumping around here. So we have lots of movement already from these particles. And if I was a good TM operator, I could definitely get some atomic resolution on this. So I'm going to give it a try, but I do warn you that I'm a very bad TM operator. But let's give it a shot because things are looking pretty good here. We actually have some spots out here. Is that visible?
It is just barely. Admittedly, there are probably some bandwidth-related pixelation things going on here with transfer. So just we'll take your word for it. Yes.
Yeah, that's a bit unfortunate. I wouldn't want you to only take my word on it, but I do see some spots every now and then out here.
Yeah,
But
certainly we can see that bright spot. We can see it on our end.
We do have 20 nanometer particles in only 40 nanometer liquid here. And then we have 18 nanometers of nitride around it on both sides. So we're really looking at some of the absolute best conditions you can ever get when it comes to silicon nitride chips and the resolution that you can achieve. The TM is the limiting factor here, and especially the operator is quite limiting right now. I'm trying now to correct the objective a little bit. Maybe I have luck with it, maybe not. Yeah. Going the right way. Cool. So there we have the spots again. Does it show up to you? You have some out here.
Yeah, a little more difficult to see it right now, but
Yeah. Okay. There we go. All right. But you know what I'll do? I'll take an image of this and I can send it later and we can add it to the recording later. So there will be some definite proof. I can tell that it is going to be difficult seeing it through the screen here.
yeah, you may even have it and then drop it into the chat. Everybody can see the chat at this point. So that's also one way to do it.
Yeah, I would like to do that, but the computer here does not have internet, so
Ah,
I'll have to transfer it later,
no
unfortunately.
problem. No problem.
Yeah. What I can do is take this image into ImageJ. That should be a good way, actually. Let's see. Give me just a minute, and hopefully I can make unequivocal proof uh, of what I'm seeing here.
And maybe if while you're working on that, can you also speak to the sample is clearly moving. Can you comment on whether that's drift related or if that's actually liquid flow related, what we're seeing on the screen?
This is a little bit of both. I think the holder is still stabilizing. It was it varies a little bit how fast it stabilizes. Sometimes 10 minutes is enough. Sometimes it takes a bit longer, and it looks like that's the case now. We just inserted it, I guess, a few minutes ago. But normally I would give it half an hour for stability, just as the temperature is aligning with the TM temperature. If we want to see particle movement, we saw a lot of that in the beginning, actually. You can see now that when I move to a new area, it's really creating some dynamics. And for people not used to doing liquid cell TM, you can just watch this dynamic for a while. It's quite interesting. The beam affected, of course, and then there's naturally some Brownian motion as well. And then there's charging of the sample, and there's all kinds of dynamics going on. All right, this is the FFT of just now. There's definitely some bad alignment, but what do you think? Can you see it?
Unambiguous. I can see the spots for sure. For sure.
All right. And that's with a bad operator on a 20-plus-year-old Tech9. But I'm actually kind of proud. I used to not be able to do this, but I had to learn a little bit. So here we are. Yeah, that actually summarizes what I have. We've shown that we can load the sample on the spot, like we've done hundreds of times in this exact way, and get atomic resolution. Yeah, so I think a good way, if any of you watching are interested in this, feel more than free to reach out to either me or Kyle or Jeff at Rave. We're happy to talk to you, and we're happy to, evaluate, do we have some interesting experiment that we can actually enable. We're more than happy to talk about that, so please feel free to reach out. You'll find our contact at insightchips.com, and of course there's ravescientific.com as well.
Exactly. Perfect way to kind of summarize.
I appreciate it. Yeah. I came in at the end. Great job, Kyle and Emma. It was really not the end, but I came in maybe 10 or 15 minutes. But I would just wanted to add to Emma's message that if there is interest and you are in this area of research, and this technology would enable and give you access to a TM and obviously enable your area of research, call us, because if we do have conversations with customers, then we are in a position at times to let you try a holder out, no strings attached. That we have to get into more of a conversation about, what your path is and what your area of research is, but we are open to doing that for the right customers. So, but with that said, great job, guys, and wanted to thank everybody today for joining us. Really appreciate it. Thank you.
Perfect.
Yeah, same from here.
Thanks, Jeff.
Thank you everyone for joining.
Yeah, I guess if there's no other questions at this time, we will go ahead and end the event. Like we said at the beginning, this was recorded, so we will make the link to the recording available. Feel free to share that with colleagues and collaborators. And if there's any other questions, you'll have our contact information, and we'll do a quick follow-up to everybody that registered and attended today. Thank you again. And with that, I'm going to go ahead and close the session for now.
You, Kyle.